And so I'm Andrea Avanzini from the University of Brescia, Italy, and today I will present our research on the characterization of a 3D printed photopolymer. So first of all, the material that we have investigated is created with the name Tango Black Plus, and it is a flexible elastomer. The flexible elastomer, which is available to the polyjet technology. This is a process based on photopolymer jetting, and droplets of this photopolymeric resin are deposited onto the printing bed. Then they are cured using an ultraviolet lamp. And a key feature of this process is that it is possible to print multi-material parts. So the combination of flexibility of the material and multi-material availability make this material attractive, for example, for flexible parts like soft robotics and some kind of biomedical devices. As well, in literature, there are examples for metamaterials and shape memory 4D materials. Thanks to the multi-material capability of this technology, one field of interest is that of the biomimetic composites, where we try to reproduce with a 3D printed structure the organization of some natural materials, which usually consist of combination of stiff and soft constituents. And in our case, the context in which we developed this characterization of the Tango Black Plus is a previous investigation on the development of novel damage-tolerant architectures, which are inspired by the Necker toughening mechanism, where basically we have a mineral layer, which is embedded into an organic polymeric soft matrix. And in the 3D printed version of this composite, obviously the Tango Black Plus plays the role of the matrix, so it supports a rigid phase up to large strains, and it also helps in terms of energy dissipation and contributes to some fracture mechanism. And this is why we investigated the behavior of this material, considering more in detail time-dependent and cyclic behavior. So the final goal is to improve the accuracy of the models that we have previously developed of this composites. So the material has been studied before, so we have already carried out uniaxial tension, some fracture tests on single-edge notched specimens, and equibiaxial tests, which were carried out on an in-house biaxial test rig that we have available in Brescia and that we designed a few years ago specifically to test soft materials. And considering specimens that were printed flat onto the printing bed, we carried out this test mainly to verify whether there was some kind of anisotropy, but at least in the planar direction, apparently the material is isotropic. So what we have done in the current work is a less, let's say, conventional characterization. So characterize the time-dependent response. We combine a uniaxial tension test with different strain rates and step stress relaxation test. So we have a stress relaxation, but at increasing load level. For the cyclic response, we carried out tests repeated cycles, either over a fixed stress level or with a stepped procedure in which the load level is progressively increasing. Now, coming to the results, considering uniaxial tension tests at different strain rates, we can see that, as may be expected, the behavior is highly nonlinear, and globally, the response seems to get stiffer as the strain rate increases. On the other end, we also observed that the ultimate strain at failure showed some dependency on the strain rate and actually the test that provided the lowest strength and the lowest ultimate strain was the one that was carried out with the lowest strain rate. Now, considering step stress relaxation, here the goal is to check whether the relaxation response is dependent on the applied strain level. And in this case, we have one specimen that is tested with increasing applied strain, and then it is relaxed. So what we observed is that actually the relaxation response seems to depend on the applied strain. So from a modeling point of view, that's an indication that we have to consider a viscous response taking into account a non-linear viscous response. Thank you. So we also observed a reduction of the strength, so the specimen failure prematurity with respect to what we were expecting. Now, considering cyclic loading, when the specimen is cycled over a fixed load level, there are some typical features like hysteresis and residual strain that we might expect for this type of material. And actually, the material exhibits some softening, not so marked, and apparently this is concentrated in the very first cycle, and then we get a stable response. Considering the uniaxial step cycle test in which the load is increased in the different phases, so the material is loaded and then unloaded. Again, we observe the presence of hysteresis and of residual strain, which reasonably gets larger as the load level increases. And if we consider this indication from a modeling point of view, this seems to suggest that some irreversible deformation is probably present. So viscous response should be combined with something like, for example, a plastic behavior. If we look in more detail to the loading and unloading paths during this very first cycle, we can see that there is a sort of Malins effect. I would say it's rather mild, but what you see is that when you unload and reload the specimen, when the specimen reached the peak stress that was applied in the previous cycle, then apparently it follows the same curve as the virgin material. From a modeling point of view, I would say this is a secondary effect that maybe is not so necessary to include in a model. So what we have gathered in terms of experimental evidence is that we have a complex material in which we have a strain rate sensitivity. We have a nonlinear viscous behavior. There is some cyclic softening, Malins effect, and there is a residual strain upon cyclic loading. So our idea is to investigate whether viscoplastic models can actually model this type of response. Taking into account that in the previous works, we have used simply a hyperelastic constitutive load. So this type of models are quite complex, but basically they consist of combination of branches in which we may have, let's say, springs and dashboards. And these models typically require a significant number of material parameters. So for model calibration, we use the software, which is M-calibration, which was fed with all the data that we have gathered from the different type of tests. So the idea was to try and see whether it was possible to identify a unique set of material parameters with which we can replicate all the different tests that we have carried out. So here you can see the Bergstrom voice, which is well established in literature. It consists basically of two networks. The first network is a nonlinear hyperelastic spring, and the second network is a sort of nonlinear Maxwell element in which we have a further hyperelastic spring in series with a nonlinear viscous element. So this model requires for its calibration 9 material parameters. And another model that we have considered is the so-called free network model. In this case, the main difference is you have an additional nonlinear maximum model. So that means that potentially you have improved your predictive capabilities, but at the price of more material parameters to be determined. In terms of fitting capabilities, you can see the fitting of Bergson-Boy's model against the strain rate. You can see that qualitatively the results are, let's say, good, but for this specific type of test, we found that you have to choose whether you want to be more accurate for the highest strain rate, or you want to be more accurate for this test run, which were ran at this lowest strain rate. On the other end, if you consider with the same set of material parameters, the other type of responses, for example, here you can see the prediction for the step stress relaxation. And here are the predictions for the cyclic response. I would say that the model actually performed remarkably well, considering the complexity and the differences between the various combination of loads that of load cases that we try to reproduce. So in general, what we found is that in principle, the more different type of data sets you provide to your fitting algorithms, the more potentially you can be more accurate in your prediction, but it may be difficult to reach convergence on a single set of material parameters. And one example is this prediction. This is for the free network model. In this case, you can see that the prediction of the cyclic response or of the step stress relaxation is, I would say, excellent, but the material parameters that we use are different. So in this case, we're not able to find a unique solution. So what we are trying to do now is to implement these models within finite element simulation. In particular, we took the equibiaxial test as a test bench. And actually, it seems that these models work fine. Here we can see the prediction of the force against time for the Bergson-Boy's model. And DBM stands for a modified version where the minus effect is taken into account, but you can see there's basically no difference. And finally, I would say the next step is to enrich this model with XFEM, trying to reproduce the failure that we observed experimentally, where actually in the biaxial test, we have the propagation of a crack from the fillet that is usually present at the connection between the perpendicular arms of the cruciform spaceline. So the final goal is actually to use this type of characterization, this type of constitutive law in a more complex model of the whole composite material studies, in which, as I mentioned before, we have used up to now a hyperelastic law. And these are the conclusion, but they're basically a summary of what I've exposed before. So thank you for your attention.